of determinants. So, for example, if you find the determinant of a matrix and then you transpose the matrix, the determinant's the same. So, if you take a matrix, we'll do an easy one. Okay, so what's the determinant of this? So the determinant is 1 times 5 minus 2 times negative 1, so 7. And then if we did a transpose, one times 5 minus 2 times negative 1, 7. Okay. And that works for every matrix. So if we transpose a matrix, the determinant stays the same. Okay, so that's an example. So we're going to go through different types of, if we do a row reduction, what happens to the determinant? If we take the inverse, what happens to the determinant? And things like that. Multiply two matrices. So we've got a list, and we'll just start this list. So the first property of determinant. The determinant of a triangular or diagonal matrix, which I'll tell you what those are in a second, is the product of the entries on the main diagonal. So this matrix is called a diagonal matrix. So what's a diagonal matrix? Like the identity, it has numbers on the main diagonal and zeros everywhere else. So that would be a diagonal matrix. So the determinant is just found by multiplying that diagonal. Okay. And if you went through the process, you would actually see that anyway, because what do? We would do this main diagonal multiplied, and then the off diagonals, we multiply those, and they're all 0. And then going backwards, we're going to hit a 0 with each going backwards, so there's nothing left. Then we have what's called an upper triangular matrix. And then there's such thing as a lower triangular matrix, which you can imagine what that would be, the opposite of this. So an upper triangular matrix has zeros below the main diagonal. And it could have zeros above too, but not all zeros. So the determinant is still found by just multiplying the main diagonal. So 1 times 5 times minus 1 times 3. And then lower. So I just put a 0 on purpose on the diagonal, because it can have zeros other places. It's just that above the main diagonal is all zeros. So if these three in a 3 by 3 are zeros, then this is called a lower triangular matrix. and this would be called an upper triangular matrix as long as the numbers below the main diagonal are 0. It doesn't matter if some of these other numbers are 0. What would the determinant of this one be? 3 times 0 times 5. So 0. And when the determinant's 0, what does it mean? That it has no inverse, and that means it's called, do you remember what a matrix with no inverse is called? Singular, right? So I said the inverse is like its partner. If it doesn't have a partner, it's single or singular, right? So that's how I always remembered it. Okay, 2. Can you guess? So if we multiplied a whole matrix by 2, does it multiply the determinant by 2? It's not. So this is say it was let's just do a 2 by 2 because you can see what happens, okay? So an example, so if I said A was 1, 3, 0, 6. The determinant of A is 6. Correct? What if I multiply that, if I did like 3A? Is this 12? No. Why not? How many 3's do we actually multiply by? I don't even, what's 3 times 18? 54? Is that right? 54. So how much bigger is that? 9 times bigger. So the rule is actually the determinant of 3A is 3 squared times the determinant of A. And that's really because you multiplied both rows by 3. So what if it was a 3 by 3? You would multiply by 3 cubed, or 2 cubed, whatever the constant was. So what's the formula up here? C, what size is it? N by N. So it just in general, C to the N determinant of A. Which kind of leads us to thinking about a row operation. Like if you divided a row by 2, one row by 2, then it would divide the determinant by 2. But if you divide the whole matrix by 2, then it's divided by 2 however many times there are rows. So here's a question. If the determinant is 6 and A is a 3 by 3, then what is 1/2, determinant of 1/2 times, negative 1/2 A? Negative 1/2, how many times? 3 times the determinant of A, which is 6. On tests, people get that one wrong all the time. Okay, third property. What if a matrix, any size, n by n, has a row or column all zeros? Zero. If you think about a 2 by 2, you go forward 0, backward 0. 3 by 3. All right, think about all these diagonals. This one has a 0, this one has a 0, and this one has a 0, right? And when you go backwards, you're going to hit that 0 each time as well. So if there's a row or column of zeros, no need to do anything. You just say the determinant 0, right? Four. Well, what about a matrix with 2 rows or 2 columns that are equal? So look at a 2 by 2, just to start. 0. Now it actually works for it still works that way for this, because you're going to hit these numbers each once in each diagonal. Once forward, once backwards. The rest of the numbers are all the same. So for example, you're going to hit that forward, 1, 2, and -2, and you're going to hit that same thing backwards, 1, 2, and -2. Because these are the same, you end up hitting these numbers each on the forward diagonals, and then these numbers each on the backwards diagonals, and it ends up being 0. So the determinant here is equal to 0. The other thing you can think of is a row operation. If you have 2 rows that are the same, when you subtract them you get a row of zeros, and a determinant of something with a row of zeros is 0. And a row operation, which I'll write down as a property later, but adding 2 rows or subtracting 2 rows or adding a multiple of one row to another row doesn't change the determinant. So you can do that row operation to any matrix, and the new matrix and the original one will have the same determinant. So that is here, matrix with a row or column . Zero again. So they can be the same 2 rows or columns. So that goes for columns as well. Like if we had 1, 2, 3 here and 2, 4, 6, and it doesn't matter what's here. All right, so the 2 columns are the same. Those determinants will all be 0. Maybe harder to think about this because it's not you don't do column operations. There's no such thing as. But remember, I said the very first thing I said, we didn't write it down yet, but is if you transpose a matrix, it gives you the same inverse or the same determinant. So transposing this will give you 2 rows the same. So 2 columns the same does give you 0. And you could try them and see. 6. If 2 rows are interchanged. So let's look at a 2 by 2 because we can take the determinant easily. And if I said B, so switch row 1 with row 2. So what's the determinant of A? 3 times 2 minus negative 1 times 4. 10? Here? Negative 10. So what happens if you interchange two rows? The determinant has the opposite sign. Okay, so why would this be useful to know? So say, for example, with this matrix. If I swap row 1 and row 2, I have the triangular matrix, and then we know the determinant without using any longer method. So, for example, I want the determinant of A. If I make a new matrix out of it, so I'm going to interchange row 1 with row 2. 1, 2, 3, 0, 1, 4, 0, 0, 6. This one has determinant 1 times 1 times 6, right? So the original, the one we're looking for, would have determinant minus 6. So that's why it's useful. As long as you keep track how many times you switched rows around, then you would know what the sign. Because if we then switched another row, you know, you could think of this, if it was a 5 by 5, and by making a couple switches, it ended up being a diagonal or a triangular matrix, right? So if you switch 2 rows, and then 2 other rows, then the sign is actually the same. But if you made 3 switches, then it would be a negative, right? Seven. Determinant of A times B is the determinant of A times the determinant of B. Easy. And I won't show you an example, but you could do that and verify that it's actually true. We're going to use that in a minute for other things. Okay. So, an example before we go to the next properties. Suppose A and B are 3 by 3 matrices with determinant of A is 5 and the determinant of B is negative 1. Find Okay, and then we'll add more properties, and then I could ask another question like this. So, the first one. So it matters what size they are. But here it doesn't. The determinant of A times B is the same as the determinant of A times the determinant of B. So this would be, determinant of A is 5, and B is -1, so -5. What about this one? Be careful, this is the one everyone gets wrong. Right, this is 3. How many times do we multiply by 3? 3 times, there's 3 rows. So this is 3 cubed times the determinant of B. -1, so -27. Right, so be careful of that. Even though you know it, I think when people see the 3, they just want to write 3. Look at this one. It's the same as a 3, but the number multiplied in front is a -1. So we'd have -1 3 times the determinant of A. A squared? 25? No. Yes? Yes, it is. Yep. It's A times A. Right, so it's still A squared. You could think of it as squaring it, or you can think of it as determinant of A times determinant of A. But it is A squared. And if it was A cubed, it would still be the determinant of A cubed, because it's multiplying it that many times. All right, so here we go. 2 to the cube because of the size. Determinant of A, determinant of B, determinant of B. You could write it out long that way. So this would be 8 times 5 times -1 times -1. Oh, thank you. Times -1. -40. Okay? Not so bad. Okay, property 8. Determinant of A inverse is 1 over the determinant of A. So we're actually going to do like a little proof for this one. I don't require you to do proofs on tests, but I'll just show you. So if we took, for example, A times A inverse, what's that equal? I. Now what if we took the determinant of each side of that? So the determinant of A times A inverse is equal to the determinant of I. I is a diagonal matrix with 1s down the diagonal. So what is the determinant of I? 1, because it's a diagonal matrix, so 1 times 1 times 1. It doesn't even matter the size. It still always has 1s down the diagonal and 0s everywhere else. So, and this would be the determinant of A times the determinant of A inverse equals 1. So if we solve for the determinant of A inverse, we get 1 over the determinant of A, which is just saying it's a reciprocal. So, for example, if determinant of A is 2, then the determinant of A inverse is 1/2. Just the reciprocal. Okay, 9. How many of these are there? This is like the never ending. There's lots. Determinant of A transpose, finally, is the determinant of A. Okay, so example. Let A, B be 4x4 matrices. There we go. You should be able to do these all easy, right? This is not hard. We're doing row operations next, which is a little bit trickier. Determinant of A times B. Minus 3 times 2. A inverse. Negative 1/3. It's the reciprocal of that. 3 to what power? 4 times the determinant of B. So 3 to the 4 is 81 times 2, 162. A transpose times B. Well, A transpose is just A. A times A inverse? 1. It's equal to I is 1, or you could multiply the 2 and get 1. Here. So, this would be determinant of A, B inverse, 1 over determinant of B. A squared is determinant of A squared. You'd write it out twice and multiply, which is the same thing. And this would be determinant of B 3 times. So determinant of A, 1 over determinant of B, determinant of A squared, and determinant of B cubed. So what does this give me? A big number. Minus 3 times 9 times 8 over 2. Minus 3 times 9 times 4. 12 times 9, 90, plus 18, 108, negative 108. Correct me if that's wrong. Okay, so we'll stop this video. This is the next part is a logical stop. We're going to do row operations and how it changes the determinant next, and then that would be it for today.